Welcome to Titrations. Really excited to go through this with you guys. It's nice that you have some experience with this and so you know what we're talking about. The titrate is a solution that we know. So for instance, when we were working with the different acid base indicator and everything all together that made our titration, when we did this, the titrate is the one that we know of the two. The analate is the solution we don't know. So, for instance, in the analate, you might know just the volume, but you don't know the concentration. And so that's what you're trying to calculate. What is the point of titration? You're trying to calculate an unknown concentration. And so our indicator is the chemical that we add to be able to let us know visually when is the pH at a specific level or point that we're like, okay, now we're good to go. And that's basically a titration. You've got it all there. The burette, the titrant, the analate, it's all there. And the reason why we call it the titrant is because we know both the concentration and the volume. But let's keep going. You will be asked to do one of these on the AP test, likely on the FRQ, and it's really good to know this equation. This equation is not on our sheet. I don't remember it being on the sheet, and so if I were starting the test, it might just be a good idea to first thing write down a few things that aren't on there, like the shapes of molecules, and N1V1 equals M2V2. It is such a simple equation, and it'll save your bacon. And sometimes you're lost, and you're like, oh, what do I do? And just plug your acid and base into M1V1, M2V2, and be like, oh yeah, I'm missing one of these things, and then you can solve for it, and it's easy. And so if you're stuck on an acid base problem, you might want to just try throwing this around and see if it works. Indicators. Now, we worked with phenolphthalein in the past, and that has a higher pH value, and so this is for if you're doing a titration and you want your equivalence point to be around a 10, 8, well, it's 8 to 10. It starts to turn pink at 8. And so if that's what you want, then you're going to use phenolphthalein. We also have bromethyl blue, which starts out as yellow and then turns blue at 8. We've got methyl red, bromescal green, methyl orange. Methyl orange is common for 4, a pH of 4. And it's really like, what pH do you need your titration to end at and to measure? And so, for instance, if I'm trying to do a titration that has an equivalence point around 8, I do not want to use methyl orange because it's not even close. I can't. Once I get over to 8, it's just the whole solution's going to be orange. And so it's really important that when you're doing this, you make sure that you're choosing the indicator that matches your outcome and what you're trying to achieve. Titration curves look just like this. And I loved that this had both what it looks like with a strong acid and when there's a weak acid. It's because it's two different shapes. And it's important to recognize that because that's going to help you a lot to be able to be like, oh, okay, I've got working with a strong base. And you're going to find out that there are shortcuts you can take when you know what the graph looks like, and it's going to save you so much time on the test. All right, so we are here. I'm going to strongly suggest that you draw each one of these curves. They're not perfect, and that was one thing that I didn't love about this diagram. It's a little bit of an oversimplification, but it helps you to realize how these work. So for instance, when I have a strong acid and a strong base, the equivalence point is going to be a pH of 7, right around water. That makes sense. Strong acid, weak base, my equivalence point is going to be less than 7. Think of the arm wrestling between the acid and the base. Strong acid is going to win. It's going to be a pH less than 7. Weak acid, strong base, pH equivalence point is going to be greater than 7, and you can see that here. I'm just showing you it with my mouse. A weak acid and a weak base is at 7. And you can see the same trends here. Strong base, weak acid, strong base, strong acid, weak base, strong acid, weak base, weak acid. And you can see those same trends Well, the stronger one is going to have the equivalence point in that range. And so, and if it's strong, then you've got 7. Now, I want you to look at this. If you need to pause the video, whatever it is, tell me what type of situation are we looking at? Where do we start? Where do we end? Is it strong? Is it weak? Tell me. All right, pause. Make your guess. The answer is a strong acid, and then we're titrating with the strong base. And so we start out as an acid here, and then we turn into a base. Our equivalence point is right at 3, which means it should be at about 7, and that looks perfect. Okay, so this one is the reverse. We've got a strong base, and then we got and mixing with a strong acid. Our equivalence point is 3, and that's really important to know. And you can sometimes the problem will be like, it'll give you 2 things. You're like, oh, what is the third thing? And all you have to do is look down at your graph and be like, oh, I have 20 milliliters of, in this case, you would have 20 milliliters of the HCl that you've added. And it just depends on the problem, on what you're adding. If you're adding the acid, if you're adding the base, it just depends on, and you're going to have to be conscious of that. But the bottom of this graph often is going to tell you how much of your volume you're adding, and it's going to be to that equivalence point. All right, pause the video, guess, and see what is this one? Strong, weak, what's going on here? All right, you're back. We've got weak acid, strong base. And you can see because of this weak curve here, and then it goes really fast and it goes really intensely up. Number 2 is a magic spot. And for the people who are taking notes at home, etc., watching this video, over top of number 2, I want you to write that the pH is equal to the pKa. That's what's happening right there at number 2. That's some magic. And you're going to be able to use that information to be able to go over to the graph and be like, okay, the half equivalence point where pH is equal to pKa is approximately a pH of 5. And so my pKa value would be 5 here. And we call this the half equivalence valence point. Okay, and it's a very important value when we're talking about titrations, and it's going to be such a massive shortcut. Massive shortcut. What is happening here? Okay, I was trying to bold this so that you guys could see that here. Bolding it. Go over here, give it the color red. We've got pH and pKa as a half equivalence point. That's it. Yeah, it's good stuff. And that's a really great shortcut. And so the question is, does this make a buffer? A weak acid, a strong base? Yes, it does. Where is the equivalence point? The equivalence point, 1, 2, 3, or 4, it's number 2. Sorry, the equivalence point is number 3. That's the equivalence point. And one of the ways you can know that number 2 is the half equivalence point is if you go, you're like down here, like, okay, 20 milliliters is what it took to get to equivalence. Half equivalence is at 10, and then you just follow the graph up, and it's really straightforward. Where's the half equivalence point? You guys know it's number 2. Why is this important? It's because pH is equal to pKa. I was going to add a little bit more on this slide. I decided against it because really that's what you need. Now sometimes the EP test might get a little tricky. And one example here, we've got a weak base with a strong acid. They might say, okay, well, what is the half equivalence point here? What is the pH or the pKa? If they ask you what the pKa is for this, that's easy. You can go here. There's the half equivalence point. Go over. pKa it's just over 9. Okay, it's around 9. But here's the scary thing. They could then ask and say, okay, well, what is the Ka? And then you'd have to be able to estimate and be like, okay, it's about 9. And then you'd have to know how to do the math to be able to work backwards and get the Ka. You guys practiced 8.1 so much where you would go from something that was a pH and you would turn it back into its original concentration. And all you had to do was 10 to the power of the pH, or in this case, the pKa, and it will give you the Ka back. And so that's a little shortcut. The other thing that I was never explained well to me, that just the AP test explains and is like, assumes that you know. Let's make that assumption. Is this a buffer? Yes, because it's a weak base, strong acid. Okay, I better change this. Weak base, strong acid. There we go. Where's the equivalence point? You guys know that it's at number 3. Equivalence point. Where's the half equivalence point number 2? Why is it important? Because that's the spot where the pH is equal to pKa. Now, one of the questions on the quiz says, hey, what is the pKb? And you're like, wait a second. And what you're going to have to do is you're going to have to be like, okay, use this information, use this same graph. What is the pH? The pH is about a, let's give it a 9 right there. We'll just round and say it's about a 9. Okay, so if the pH is a 9, then the pOH is a 5. And now you can use that information to be like, okay, well, the pKb is actually a 5. And then you can go 10 to the negative 5, and then you've got your Kb value. So it's kind of wild how that all works, but I felt like no one ever showed this to me. And in fact, I was really disappointed. A lot of the videos that I watched and the research I did didn't have this line right here. They left all of this out, and they just assumed that you guys would be able to do that without anyone explaining it to you. So that kind of made me mad, but we do what we do, and we make it work. So let's go to the diprotic acid curve. This one, I haven't seen this come up, but they're like, you have to teach it. That might come up on the test. A diprotic acid curve is where you have a titration that's going through the motions, and it's normally would just be this one nice curve and then it would be done. But if you look, we've got a second curve. Why is that? Here we've got the this is for sulfuric acid. So it's H2SO4. And it's the reason why is because as it sheds the first set of hydrogens, and then you get your, what would that be? Your conjugate base would then, let me see if I can type this out. I think it would be easier if I do that. And I'll start here, and I'll just say, okay. So when we're at point A, it's mostly all H2SO4. And then once we get to point B, we start to make a whole lot of the conjugate base, which is HSO4 1 minus, okay? And let me just kind of play around with this so that you guys can see better what's going on, okay? So that's our conjugate base, and we start making it, and then it becomes the acid in the next curve under C. So in C, we're now, in C, we're changing, the acid has become HSO4, that conjugate base, that ion is now the acid, and it's now shedding its proton. And once we get to D, okay, it becomes the acid, okay, and now we're into the approaching equivalence point number 2. D is when we start making a whole lot of SO4 2 minus. Let me see if I can, yeah, there we go. All right, so let me put this up here so that you can see it. So we start out, we have our acid of sulfuric acid, and then at B, we start to make our half equivalence point. We start to make more of our conjugate base, which is the HSO4. Then it becomes the acid, and it starts to shed its proton. So we lose one proton, now we're losing the second proton, and now we're done because we've ran out of protons. And we're at SO4, this is where it's all base. Here at F, all we're left with is SO4 2 minus. So that's what a diprotic acid curve is. Here's the question. We see 2 curves on an H2SO4. How many curves would we see on a phosphoric acid or H3 at PO4? Pause it. Tell me, how many curves would we see on H3PO4? The answer is you would see 3 different curves because there's 3 hydrogens on the front. They would shed, and then they would shed, and then would shed, and they would yeah, they just keep shedding until they run out of hydrogens, and all you're left with is the PO4 ion. Team, really excited to go through this and help you guys finish Unit 8 strong. Thank you so much for your hard work. I wish you success. Take care.